Here's the introduction to the unit on permutations and combinations. So in this unit, the last unit of Math 12, we're going to be looking at how to count things. And there's many problems in probability and statistics that need a careful analysis of complex events. Combinatorics' basic roots are to develop systematic ways of counting. These systematic counting methods will allow for solving of complex counting problems that are useful in all facets of life. So let's just say we're going to a restaurant. We have a cafe and there's a lunch special. We're allowed to choose one of two different types of sandwiches, either an egg sandwich or a ham sandwich. And then we can try 3 different types of drinks. So we could get milk or juice or coffee. And we've got 2 choices for dessert, yogurt or pie. Now we must choose one of each category, and we're only allowed to choose one of each. So how many ways could we make a lunch special? Well, we could do this by kind of connecting the dots. There's one egg sandwich with milk and yogurt, or egg sandwich with milk and pie, juice and yogurt, juice and pie, coffee and yogurt, coffee and pie. We do the same thing for the ham. Ham with milk and yogurt, milk and pie, juice and yogurt, juice and pie, coffee and yogurt, coffee and pie. And you can see that this diagram kind of gets complicated and messy pretty fast. So an easier way to analyze this or to put all this information together is in something called a tree diagram. So to make a tree diagram, I can first draw a branch that represents my choice of sandwich, and then my choice of drink, and then my choice of dessert. So for sandwiches, I've got 2 possibilities, either egg or ham. Now with that egg sandwich, I can get 3 different drinks, milk, juice, or coffee. For ham sandwich, I can also get 3 different drinks, milk, juice, or coffee. And then for each of the drinks, I've got 2 different choices of dessert, yogurt or pie, yogurt or pie, yogurt or pie. Okay, so each branch of this tree represents a different meal option. So this branch here would represent the possibility of getting an egg sandwich with coffee and yogurt. Whereas this branch here would be a ham sandwich with juice and pie. So now I can count out how many end branches I've got. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 possibilities. So you can do a tree sideways like that, or you can do it vertically. So it'll be like EH. Each one has M, J, C. And then JP. And you're just counting the ends of the tree to find out how many options you have altogether. I think it's more clear if I write it like this. Now, we can also use another method to find out all the possibilities without having to list them all, and that's called the fundamental counting principle. So we can just draw a line on our page to represent how many choices we have for sandwich. We can draw another line to represent the choices that we have for a drink, and we can draw another line to represent the choices that we have for dessert. So we've got 2 different sandwiches, 3 different drinks, 2 different desserts. If we multiply all those numbers together, we get the 12 meals. So we can use this when there's a lot of possibilities and we don't want to draw a tree that has like 100 branches. So if there's more than a limited number of possibilities, then we can use this principle. So if we go to an ice cream store, there's an ice cream store that has 24 flavors. You can get a cone that's regular, sugar, or waffle. And you can get 2 scoops of ice cream. So first of all, how many choices of cones do we have? We've got regular, sugar, waffle. So 3 choices of cones. For our first scoop of ice cream, we've got 24 choices. It doesn't tell us that we're not allowed to repeat, so we could have 2 scoops of vanilla. So there's 24 choices for the second scoop. So all together, we have cone, first scoop, second scoop. 3 choices for the cone, 24 choices for the first scoop, 24 choices for the second scoop, giving us a total of 1,728 ice cream. That would be a really big tree, so we would never want to do a question like this as a tree diagram. Another example, a computer store sells computers. There's 4 different monitors, 5 different printers, and 3 multimedia. So how many different computer systems can we make? 4 times 5 times 3 is 60 computer systems. So this principle is known as the fundamental counting principle. And that's just saying that you draw a line for each of the different possibilities. You multiply all of those numbers together. It gives you the total number of different ways. So we can use this to find out how many 2-digit numbers there are. So a 2-digit number, for example, is a number like 37. 3 is the first digit, 7 is the second digit. Or 45, or 22, but not 03. That would be a 1-digit number. So we could draw 2 lines, one that represents the first digit and one that represents the second digit. So the first digit of our number can be anything from 1 to 9, but not 0. So there's 9 possibilities for the first digit. But the second digit could be any number, including 0. So from 0 to 9, we actually have 10 different digits to choose from. There's 10 possibilities for the second digit. So 9 times 10 is 90. And this kind of makes sense because it's all the numbers from 10 to 99. So all the numbers from 10 to 99 would be like 99 minus 10, which is 89. Now that's kind of weird. Where did we lose a number? And you can think about it to yourself. If you want all the numbers from 1 to 5, you can count that out on your fingers. That's actually 5 numbers. You can't just go 5 minus 1. You actually have to go 5 minus 1 plus 1. If you want all the numbers from 24 to 27, you have to go 27 minus 24 and then plus 1. Because you want to include both 24 and 27. It's 24, 25, 26, 27. There's actually 4 possibilities. So all the numbers from 10 to 99 would be 99 minus 10 and then plus 1. So there's 90 numbers there. Now we'll try another example. How many 2-digit numbers can we form with just even digits? And if we're allowed to repeat digits, so that means, let's see, the smallest number I guess would be 20. And then we're allowed to repeat, so it would be 22, 24, 26, 28. This might not actually take us a long time to write out all the possibilities. 60, 62, 64, 66, 68, and 80. So you can see 1, 2, 3, 4 columns, 5 rows. We have 20 different numbers. So using the fundamental counting principle, we can do first digit, second digit. Again, we're not allowed to begin with 0 because that would make it a one-digit number. So we have 1, 2, 3, 4 numbers to choose from for the first one. But for the second one, we are allowed to choose 0. So we've got 1, 2, 3, 4, 5 options. 4 times 5 is 20 ways, just like we wrote out. Now, question B is, what if repetition of digits is not allowed? So we're not allowed this one, this one, this one, or this one. So that would be the same as part A. Take away those 4 numbers. So 16 ways. But how can we do that using the fundamental counting principle? You've got your first digit, your second digit. Your first digit cannot be 0. So it could be any of the 4 numbers. Now let's pretend that we took one of them. Now we're allowed to choose 0, but we're not allowed to choose the same number. So there's only 1, 2, 3, 4 numbers left to choose from. 4 times 4 is 16 ways. Example 4, a true-false test has 7 questions. The answer to each question is a guess. How many possible answers are there for each question? So because it's true or false, there's 2 possible answers. Either you can answer true or you can answer false. So how many different ways could you complete the test? Well, you could guess all the answers are true. Or you could guess that the first one's false and the rest are true. Or all the first ones are true and the last one's false. Or false, true, false, true, false, true. It would take me a long time to write out all the possibilities. But I can do this using the fundamental counting principle by saying first question, second question, third question, fourth, fifth, sixth, seventh question. The first question has 2 choices. Second question is 2 possible answers. And each question I can either answer true or false. 2 times 2 times 2 times 2 is 2 to the power of 7, which is 128 ways that I could answer that test. There's only one right answer, so the probability that I'm actually correct is only 1 out of 128. A measly less than 1%, 0.78%. So less than 1% chance that I get all the answers right. Now what if the test was multiple choice? That means I have 4 options for each question. A, B, C, or D. So how many ways could I answer this test? Well, I could answer them all A's. Or I can guess that the teacher never starts with A. Maybe they love the letter C. Or it could be C, B, A, B, C, D, C. There's so many possibilities. I can do this using the fundamental counting principle. The first question has 4 answers, so does the second. Each question has 4 possible answers. So there's 4 to the power of 7 ways that I could answer this test. 16,384. Wow. So I only have a 1 in 16,000 chance of guessing the right answer on a 7-question multiple choice test. Very, very, very small chance. I'm almost better off playing the lottery. Now these sorts of questions have a lot of real-life examples and applications. For example, I don't know if you know, but like 8 years ago in Vancouver, we didn't have to always type in the area code when we called a friend. I would just dial 584-1036 instead of 604 before the number. So a lot of city planners need to be able to find out how many possible numbers there are and compare that to the size of the population to know how many digits they should include in their phone numbers or in their license plates. For license plates, you need to know how many cars will be on the road so that you can have enough unique license plates. So let's just see how many license plates we could create with the system that we have now that has 3 letters and 3 numbers. So we'll draw 3 lines for the letters. And then 3 lines for the numbers. So there's 26 letters in the alphabet. And it says we're allowed to repeat letters, so we could have something like M. There's 26 possibilities for each letter. We're allowed to repeat numbers, so all together I've got the digits from 0 to 9. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 digits. And I'm allowed to repeat. So if there's no restrictions on license plates, then I can make 17 million different license plates. All that's got Vancouver covered, no problem. Now, but if you live in China, that's about the size of Shanghai. Now, what if no letter or number can be repeated? So we'll draw this using the fundamental counting principle. Maybe I'll just line it up the exact same. So we've got letter, 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 number, number, number. So for the first letter, I can choose any one of the 26. Any letter from A to Z. But now after I've chosen a letter, I'm not allowed to choose that one again. So now I only have 25 letters to choose from. And after I choose another letter, I'm not allowed to choose that one again either. So now I only have 24 options. Same thing with the numbers. For the first number, I can choose any of the numbers. But after I've taken that one out, I only have 9 choices left. And then after I've taken another number out, I only have 8 choices left. So if I'm not allowed to repeat, then I have much fewer license plates. 11,232,000. Not enough for Beijing. Now, what if a letter can be used twice, but not 3 times? So this is actually quite complicated. If I'm trying to think of all the ways that a letter can be used 2 times, then, well, let's see. That would include license plates like AAB 929 or ABA 929 or BAA 929. And then I would also have to include the ways that I could use a number twice. But that kind of gets complicated. There's so many different ways that I can rearrange those. So maybe if I think backwards. Let me start with all the possibilities, which we found in part A, and take away all the ones that are not allowed. So all the possibilities was 17 million 576,000 license plates. I'm going to take away all the ones that are not allowed. So I'm not allowed to have 3 letters. I'm not allowed to have 3 numbers the same. So let me figure that out with the fundamental counting principle. So how would I get 3 letters the same? Well, for the first letter, I'm allowed to choose any letter from the alphabet. It could be any letter that's all the same. But then once I've chosen that letter, like say I chose the letter M, the next one also has to be M. And M. So that would give me the number of ways that I could have all 3 letters the same. And then the numbers could all be anything that they want to be. Maybe 10, 10, 10 possibilities. It could be 921 or 314. Anything's okay. Now, I could also do the same thing, have all the letters different, but the number is the same. So I've got 10 choices for the first number, but then after I choose a number like 8, then the next one has to be the same. So it has to be 8, has to be 8, one choice for those ones. Now there's a slight problem with the way I did this, because I actually subtracted, with the first question I subtracted the ones that are like MMM, but because I had 10 choices for each of them here, I also subtracted something that could have been like MMM 333. And then I subtracted the ones that have all the same number, but because I chose 26, 26, 26, it's possible that they could have the same letter. So that means I subtracted MMM 333 2 times. So I should add back ones where you have 3 same numbers and 3 same letters, because I subtracted those out twice. So that would be 26, 1, 1, 10, 1, 1. So now I plug that into my calculator, starting with 17,576,000 minus the 26 times 10 times 10 times 10, and then minus 3 letters the same, sorry, 3 different letters, three numbers the same, but then that means that I possibly subtracted the MMM 333 type of number 2 times. So I'm going to add that back in again. And that gives me 17,374,500. So your homework for this unit is from page 351, numbers 1 to 9. And in your textbook, they have an easier way to do the letters and numbers problem. I'll just put that here. You can pause the video if you want to look at that and write it down. And that's also explained in the back of your textbook.